Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
In 1963, Eugene Paul Wigner, a Nobel laureate in physics, penned an essay that continues to reverberate through the halls of science and philosophy on the unreasonable effectiveness of mathematics in the natural sciences. This work did propose a mathematical proof, nor did it unveil a groundbreaking experiment. It articulated a profound and unsettling observation, the astonishing, and largely inexplicable, aptitude of mathematics to accurately describe, predict, and explain the physical world. This effectiveness, in Wigner's view, extended far beyond mere correlation. It encompassed a predictive power and explanatory depth that bordered on the miraculous. The question posed was, in essence, why does mathematics, a product of human cognition, possess such uncanny accuracy in mirroring the universe? To elucidate this point, Wigner offered several compelling examples. Perhaps the most iconic is Newton's law of universal gravitation, initially formulated to describe the motion of falling apples and the orbits of planets within our solar system. This mathematical formulation subsequently found success in describing the trajectories of distant galaxies and the behavior of binary star systems, phenomena far removed from Newton's original observations. Such broad applicability, extending beyond the scope of its initial design, constituted the unreasonable effectiveness that Wigner sought to understand. The intellectual climate preceding Wigner's essay contributed significantly to his unease. The birth and ascendance of quantum mechanics, with its reliance on abstract mathematical formalisms such as Hilbert spaces, operator theory, and group representation theory, further amplified the mystery. These mathematical structures, initially developed without direct physical motivation, proved essential for describing the behavior of subatomic particles. They permitted accurate calculation of energy levels, spectral lines, and scattering cross-sections. Physicists were utilizing the mathematical framework to describe the physical components. Additionally, the crisis of foundations in mathematics, a period marked by the discovery of logical paradoxes such as Russell's paradox and the implications of Gödel's incompleteness theorems, cast a shadow of doubt on the uncritical application of mathematical reasoning. Russell's paradox exposed contradictions within naive set theory. Gödel's theorems established inherent limitations in formal systems, demonstrating that within any sufficiently complex system, there will always be true statements that cannot be proven within that system itself. This caused Wigner to contemplate the limits of mathematics. Wigner's central problem arose from this confluence of factors. He sought to understand why mathematics, a creation of human thought processes, could so accurately predict and explain phenomena it was designed to illuminate. He drew a distinction between empirical laws, derived directly from observation, and mathematical laws, which often preceded and predicted empirical observations. The effectiveness of mathematical laws appeared unreasonable. He pointed to instances where mathematical formalisms were developed before any known physical application. Riemannian geometry, developed by Bernard Riemann in the mid-19th century, is a prime example. Riemann's work generalized Euclidean geometry to curved spaces, an abstract mathematical concept. Decades later, Albert Einstein adopted Riemannian geometry as the very mathematical language of general relativity. The curvature of spacetime, a central concept in Einstein's theory, found its precise mathematical formulation in Riemann's earlier work. The ability of mathematics to anticipate the needs of physics amazed many. Wigner's initial attempt to resolve this conundrum proposed that this unreasonable effectiveness could possibly originate from a pre-established harmony or a deep structural similarity between the human mind and the universe. This suggestion, with its echoes of Platonic idealism, posited that the mathematical structures we discover are not merely artifacts of our minds, but reflect an underlying reality. The human mind, through its capacity for mathematical reasoning, is attuned to this reality. The philosophical implications of Wigner's argument are both profound and multifaceted. His perspective borders on Platonism, the belief that mathematical objects exist independently of human thought, and that our mathematical discoveries are akin to uncovering pre-existing truths. This stands in contrast to other philosophical perspectives, such as empiricism, which emphasizes the role of experience in shaping our knowledge of the world. The nature of scientific explanation lies at the heart of the debate. Direct influences on Wigner's essay were diverse. Gödel's work on incompleteness forced a reconsideration of the limits of formal systems. Hilbert's formalism, which sought to provide a rigorous foundation for mathematics-inspired debate. The general philosophical debates concerning the foundations of mathematics and physics in the early 20th century all contributed to the formulation of Wigner's eye. The immediate reception of Wigner's essay was mixed. Physicists and mathematicians found themselves both intrigued and challenged by his arguments. Some embraced his reflections on the mysterious power of mathematics, others sought alternative explanations, questioning the universality of mathematical effectiveness and proposing more pragmatic interpretations. The debate initiated by Wigner continues to this. Wigner's provocative thesis regarding the unreasonable effectiveness of mathematics faced a spectrum of responses, each reflecting distinct philosophical commitments. Empiricists, for instance, often characterize mathematics as an exceptionally useful tool, refined through countless applications to the physical world. In this view, mathematics is effective because it has been rigorously tested and honed by experience. Its predictive power stems from its capacity to accurately model empirical phenomena, not from any inherent connection to an abstract realm of truth. Critics point out that Newton's law of universal gravitation, often cited as a prime example of mathematical effectiveness, was, in reality, derived from empirical observations of planetary motion. Tycho Brahe's decades of careful astronomical measurements, followed by Johannes Kepler's formulation of his three laws of planetary motion, provided the empirical basis for Newton's mathematical framework. Formalism, another counter-perspective, portrays mathematics as a purely formal system, a game played with symbols according to predefined rules. In this view, mathematical statements possess meaning solely within their own internal logical structure. Its applicability to the physical world is a happy coincidence, a result of cleverly choosing axioms and rules that happen to mirror certain aspects of reality. There exists no intrinsic reason why a formal system, developed independently of empirical considerations, should prove so adept at describing the behavior of nature. Structural realism offers a more nuanced perspective. This philosophical stance suggests that mathematics effectively captures the underlying structure of reality. The universe possesses an inherent mathematical structure, and mathematics provides the language and tools to describe it. Mathematical models are successful because they mirror the abstract structural relationships that govern physical phenomena. Modern physics demonstrates this. The standard model of particle physics relies heavily on group theory, a branch of abstract algebra, to classify and predict the behavior of fundamental particles. Symmetry principles, expressed mathematically through group representations, dictate the interactions between these particles. Specific criticisms target Wigner's examples. The development of Riemannian geometry, for example, was driven in part by physical considerations. Bernhard Riemann's work on curved spaces was motivated by the desire to generalize Euclidean geometry and provide a framework for describing gravitational fields. Einstein's theory of general relativity utilizes Riemannian geometry and explains gravity as the curvature of spacetime caused by mass and energy. Alternative explanations for the effectiveness of mathematics abound. Some appeal to the anthropic principle, which suggests that we observe only those universes where mathematics is effective. In universes lacking a mathematically describable structure, complex life, and therefore scientific observers, could never arise. Other theories propose that mathematics gains its effectiveness through active shaping by scientific needs and practices. Mathematicians develop concepts and methods tailored to addressing concrete scientific problems. Wigner's essay spurred inventive mathematical advancements. It encouraged deeper philosophical scrutiny of mathematical modeling in physics. New approaches to understanding the relationship between mathematics and the physical world developed. Category theory gained increased attention as a potential framework for unifying different branches of mathematics and physics. Researchers explored the use of topos theory to study quantum gravity, seeking to reconcile general relativity with quantum mechanics. Wigner's concepts extend beyond physics. In computer science, the effectiveness of algorithms reflects a similar interplay between mathematical structure and practical application. The design of efficient algorithms relies heavily on mathematical techniques such as graph theory, linear algebra, and number theory. The success of machine learning algorithms, for instance, depends on mathematical optimization techniques that allow computers to learn from data and make accurate predictions. In economics, the limitations of mathematical models provide a cautionary tale about the potential for oversimplification. Mathematical models can assist in understanding complex economic phenomena. They require careful validation against empirical data. Wigner's legacy endures. His essay holds relevance in debates about scientific knowledge, the role of mathematics in science, and the relationship between mind and reality. It highlights the limitations of purely empirical or formalistic accounts of scientific knowledge. It urges a deeper exploration of the ontological status of mathematical entities and their relationship to the physical world. Wigner's unreasonable effectiveness presents a profound question about reality itself. The question forces a reconsideration of the relationship between our minds, our mathematical tools, and the world we seek to understand. Contemporary science and philosophy benefit from Wigner's challenge. The challenge demands a continued exploration of the nature of scientific explanation and the limits of human knowledge.
We really appreciate you tuning in to this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.